Hello, it's Dr. Daystorms once again, and this is the last of the Chapter 2 videos. And I have to apologize ahead of time right now for a couple of reasons. One, this part really requires that you just memorize things, and I always hated just rote memorization. And two, just due to the nature of chemical formulas and how to name compounds and things like that, this video will probably be a little longer than some of the other ones from this chapter. Let's go ahead and get started. We're going to talk about chemical formulas and how to name compounds. First off, a chemical formula, and we're going to talk about the two different types. There's the molecular formula and the empirical formula. But the chemical formulas tell you the ratio of the number of atoms of particular elements in a molecule. So actually, it just tells you how many atoms of those molecules there are in that compound. Okay, so for example, we have water, and pretty much everyone knows that the formula of water is H2O, so that indicates that there are 2 hydrogens for every oxygen molecule in this compound. Carbon dioxide is CO2, methane gas, CH4, so on and so forth. When we say a molecular compound versus an ionic compound, it's another type. Molecular compounds are almost always made up of nonmetals, whereas an ionic compound is going to be made up of a metal and a nonmetal. So molecular compounds tend to be from the elements from the right-hand side of the periodic table, and including hydrogen. Those are the nonmetals. Whereas the ionic is usually from an element from the left-hand side of the periodic table and an element from the right-hand side of the periodic table. We'll give some examples as we go along. Now there are 7 naturally occurring diatomic molecules. That means if you ever come across hydrogen in nature by itself, elemental hydrogen is actually H2. And unfortunately, you're just going to have to memorize these 7 molecules. And if I ask you, to give the elemental form of chlorine, it's Cl2. Chlorine gas is Cl2. So it's the 4 halogens: fluorine, chlorine, bromine, and iodine, oxygen, nitrogen, and then hydrogen. Those are the 7 diatomic molecules. You just have to memorize those. There are 2 types of formulas in general. There's an empirical formula, which just gives you the ratio of the number of each element in the compound. And it's always a whole number, and it's always the lowest common denominator. So, for example, let me change the color of this pen first. H2O is an empirical formula. There are 2 hydrogens to 1 oxygen. But if we take glucose, we notice here with glucose is C2H6O2. That's not an empirical formula because all of these subscripts, which tells you the number of elements in it, are not in their lowest whole number ratio. So for glucose, the empirical formula would be CH3O, because you can divide all of them by 2. So the C2H6O2, that is the molecular formula. The empirical formula just tells you the lowest ratio, the whole number ratio. And that's important because of ionic formulas, ionic compounds, which we'll talk about in a moment. We use their empirical formulas. And there are some other important applications later on in the semester where the empirical formula is important. But the molecular formula, it tells you the actual number of atoms in the molecule. The empirical formula is the lowest common denominator. It's just the ratio. it is possible, so for example with water, both the empirical and the molecular formula are the same. However, with other compounds, such as glucose, sugar, it's C2H6O2 is the molecular formula, but CH3O is the empirical formula. Okay? So to reiterate, empirical formulas give the lowest whole number ratio in the elements in the compound, whereas molecular formulas give the exact. Once again, it is possible for them to be the same. So another example where they're the same would be methane gas, CH4, because it's 1 carbon, 4 hydrogens. That's both the empirical and molecular formula. Whereas, if we look at ethane, which is C2H6, that's its molecular formula. But the empirical formula for it would be CH3. I'm just going to skip through this, and on the PowerPoints on your own, you can look through those. There are different ways to write formulas. The ones that we see the most often in this class typically will be either the structural or the perspective drawing. The structural formula just shows you the way in which they're bonded. The perspective actually gives you the three-dimensional aspect to it, and let me show you what that means. I'm going to draw that one, the perspective drawing, larger. So it has a carbon. This is for methane gas. It has a hydrogen. Well, it has 4 hydrogens. Let me just go ahead and draw it. It looks like that. This shows you the 3 dimension of it. Anything that just has a regular straight line like this and here, that's in the same plane as the board. Whereas, let me change colors. This hash mark here, the one that looks like hash mark, that shows you that's going away from you. It's going into the board in this instance. And finally, the one that looks like a wedge, that means it's coming out towards you. It's coming out from the plane of the board. So that's why it gives you the 3-dimensional aspect for it. In this particular structure here, it's called tetrahedral. You can imagine it being like a camera on a tripod. Okay. Two other ways. Two other ways to show the different types of formulas include the ball and stick, which is to give just a general idea of the relative bonding of the atoms. And then we have the space-filling molecule, or the space-filling model, which is actually the model that shows you the relative size and how much space that molecule would take up, relatively speaking. I've already mentioned ions in the past, but whenever an atom loses or gains an electron, they become ions. If it loses an electron, it now has more protons than electrons. Remember, it was an element. Say, for example, let's look here at magnesium. When it was an element, it had the same number. Let's see. Magnesium has 3... 1, 2, 8, 9, 10, 10. No. I'm sorry. Magnesium has, let's see, 2 plus 8 is 10, 11, 12. So it would have 12 protons and 12 electrons. However, if it loses those 2 electrons, it now has 12 protons and 10 electrons, which gives it a positive 2 charge. The way that this works here is that Please notice that I say positive 2 charge, but we write it as a 2 plus. You don't ever put the plus sign in front of it. The plus sign always goes behind it. Whereas, let's say if we have an atom like chlorine, which gains an electron, it now has one more electron than protons, and so chlorine here would have a Cl minus charge. If it's just a 1, you don't have to include the 1. If it's anything more than 1, you'd have to. For example, oxygen forms a 2 minus charge. Okay? If it's a positive number, they're called cations. If it's a negative ion, it's called an anion. The way that I remember it, and this is kind of hokey, but it helped me, was cation. The T in cation kind of looks like a positive sign. And the way I remembered anion is it has 2 ends, which are negative. Cation kind of looks like a positive. Anion has 2 ends, which are negative. Another thing that you may notice already is that the atoms on the left tend to lose electrons and they're positively charged, whereas the atoms on the right tend to gain electrons and are negatively charged. Hydrogen can do both. Also, one thing to notice is if it's in group 1, it tends to lose 1 electron to become positively charged, plus 1. If it's in 2, it tends to lose 2 to become 2 plus. And then aluminum, which is the only one in 3, it tends to be 3 plus because it loses 3. Likewise, let's see, if it's in group 7, they tend to just gain 1 electron to become negative 1 charge, and the chalcogens tend to gain 2 electrons to become 2 minus charge, and the nitrogen, if it forms an ionic bond, it usually gains 3 to become a 3 minus charge. And one thing you're going to find out later on is that the reason why they do this is that way they kind of look like they like to take the configuration of noble gases. But right now you just have to memorize those. So ionic compounds are formed between a metal and a nonmetal. So for example, sodium chloride, which is salt, table salt, is formed when we have a sodium that has a plus 1 charge because it's lost, whoops, let me undo that one. It lost 1 electron, and chloride, which has a 1 minus charge because it's gained 1 electron, and they come together because the positive charge and the negative charges are attracted, and they actually can form these crystals. Okay? That's why the empirical formula and the ionic formula are the same. It's 1 chloride ion to 1 sodium ion. 1 sodium, 1 chloride. Since these ionic compounds have to be electrically neutral, it's easy to determine the ionic formula for it. Because we've already done that with sodium chloride. If we look at the example of sodium chloride, sodium has a plus 1 charge. Chloride has a 1 minus charge. And so what we do is you take the number of the cation, it becomes the number of the anion. Likewise, you take the number of the anion, and it becomes the subscript for the cation. And so it would be Na1, Cl1, and if there's only 1, we just drop it. And so that's where we get the idea of NaCl. The example that they're showing here is where we have magnesium, which is a 2 plus, nitrogen, which is 3 minus, and so this is where the nitrogen ends up needing 2 for the molecule. I'm sorry, for the compound, and magnesium needs 3, because if you need to do it mathematically, you have 3 times 2 plus, and 2 times 3 of the negative charges. This is a total of 6, and this is a total of 6. we have a positive 6 and a negative 6. So therefore, the positive and the negative cancel each other out. Now, what happens? Let's say what happens if we have like magnesium and oxygen. You have magnesium, which is a 2+ charge, and you have oxygen, which is a 2- charge. So you would expect the oxygen's number will become the subscript for magnesium. Magnesium's number would become the subscript of oxygen. So therefore, you would think, hey, it's going to be Mg2O2. But that would be wrong, because we only use the empirical formula for these ionic compounds. So this would simplify to just MgO. That would be magnesium oxide. Again, I have to apologize that you will just be expected to memorize the common cations and common anions. Those that are let me see. Oh, come on now. Those that are in bold here are the ones that you absolutely must remember. First of all of the alkali metals, like hydrogen, lithium, sodium, potassium, and cesium, they form +1 charges. So you need to know the ones that are specifically that are in bold. So we have hydrogen, sodium, potassium, and then silver is a transition metal, but it also forms a +1 charge. Mm-hmm. You need to know the diatomic cations. So we have magnesium and calcium, but also the other ones in the same family do form that. The other one that's really important, especially in vivo, that you need to remember is zinc. That's Zn 2+, and then aluminum is a 3+. Then we have others that you need to remember as well. There's one that's called a polyatomic cation, which is ammonium. That's NH4+. That's where the nitrogen bonds 4 hydrogen first in a covalent bond formation, and that overall forms a cation that can go on and form an ionic structure. I do want you to know copper 2, copper 1, iron 2, and iron 3, mercury 2, and lead 2. On the anionic form, you need to learn the halides, fluoride, chloride, bromide, iodide, hydroxide, and it wouldn't hurt for you to know cyanide, because you'll probably just end up knowing cyanide from all of the practice problems and stuff that we do. We have oxide, which is O2-, and sulfide, which is S2-. We have a lot more of the polyatomic anions. This is acetate, chlorate, nitrate, permanganate, carbonate, chromate, sulfate, and phosphate. And this gives all of their respective charges. So let's do the inorganic nomenclature, where you have, in particular, right now we're talking about ionic compounds. You always write the cation's name first, and then you write the anion's name. Okay? If the anion is an element, you change the ending to IDE. If it's polyatomic anion, you just simply write the name of the polyatomic anions. For example, sulfate. If the cation can have more than one possible charge, like the transition metals, many of them, say for example copper, you have to put the charge in Roman numerals in parentheses. So let's do a couple of examples. You already know the answer to this one. It's NaCl. So you write the cation first, which is sodium, and it's just its name, sodium. Then you write the anion as a separate word, which that's chlorine, but we change the ending of it to IDE, so it becomes sodium chloride. Let's do another one. Okay, what about this? We have a copper and we have nitrate. This is the nitrate anion. But there's a problem. Copper can actually form more than one. This is very important. Is this copper 1 plus or 2 plus? Let's say, what happens if it's copper 2 plus? Well, if it's copper 2 plus, nitrate has a -1 charge overall. So we're going to actually first need to balance the formula for this. So the 2 is going to go down here to be the subscript for the nitrate, and the -1 is going to end up being the subscript for the copper. So let's first write it. It's going to be Cu with a 1, which is implied, parentheses, NO3, so this is just like in math, end parentheses 2. Now let's name it. So we name it as copper, but since copper can form more than one cation, we have to put in parentheses, it's the Roman numeral, showing what cation it is. This is copper 2, because it's a 2 plus, and then we just name the polyatomic anion, nitrate. So this becomes copper 2 nitrate. I would expect you to be able to go backwards as well. For example, let's do iron 3 oxide. I want to give you a moment to figure out what the chemical formula for iron 3 oxide is. Sorry, I have to take a drink. First, you need to know the chemical symbol for iron, and that's Fe. And we already know that it's 3 plus charge, and we know that because of this right here. That lets us know that it's a 3 plus charge. We now need the symbol for, well, first of all, we need to know what oxide is. Oxide is oxygen. And what is the charge on an oxygen anion? It's a 2 minus. So now, the 2 minus means we're going to have 2 of the irons. The 3 plus means that we're going to have 3 of the oxygens. So let's go ahead and let's write the ionic formula for this ionic compound. It's going to be Fe2O3. That's iron 3 oxide. What happens when there are multiple oxyanions? So the examples here are NO2 minus and NO3 minus. SO3 2 minus and SO4 2 minus. So what you do is the endings on these, if it's the one that has the fewer number of oxygens, it gets an ITE ending. That's why it's nitrite and sulfite. if it's the one that has the higher number of oxygens, it gets the ATE ending as a nitrate and sulfate. I actually have been doing this already in the sense that we've been talking about using like nitrate. So let's just do an example of, let's draw out the formula for copper. Copper makes more than one. Copper 1 nitrate. I'll give you a moment to write it out. The symbol for copper is Cu. Symbols for nitrate are NO3. Since nitrate has a -1 charge, copper has a +1 charge, the ratio is still going to be 1 to 1. So CuNO3 is the correct answer. There are a couple of oxyanions that have more than 2 forms. So for example, if we look at the chlorate series, and this is where it gets a little more tricky. You can think of chlorate as being the second highest, or like the root word. So if it has one lower number of oxygens, it's chlorite. ClO3 minus, ClO2 minus. If it has even one lower than that, so now we're 2 down from the root. If chlorate was the root, minus 1 oxygen for ClO2 minus is chlorite. If it's just ClO, so we just have 1 oxygen and still minus overall, it's called hypochlorite. Because hypo means low, like hypoglycemia has low blood sugar. If it has 1 more than chlorate, you add PER as the prefix. Similar to hyper, but this doesn't have the HI. So that becomes perchlorate. ClO4 minus is perchlorate, ClO3 minus is chlorate, ClO2 minus would be chlorite, and ClO minus would be hypochlorite. But what about acids? The way that they do the acids is if the ending ends in an IDE, you just change it to IC and add the word acid, and you call it, they add the prefix hydro. So, for example, we have hydrochloric acid, hydrobromic acid, and hydroiodic acid. And hydrofluoric acid would be HF. Because HF, you would think, oh, that's hydrogen fluoride. But since it's an acid, we say hydrofluoric acid. If it ends in an ite, then the ending becomes us acid. OUS acid. So, for example, we have here chlorite. We add a hydrogen to it. It becomes hypochlorous acid. Okay? I'm sorry, I got that backwards. If it was hypochlorite, it becomes hypochlorous acid. If it's chlorite, it becomes chlorous acid. Let's do this one. Oh, just give me a second to write it out. That's an S. So if we look at here, this would be sulfate. Okay? You would say hydrogen sulfate. But we don't, since this is an acid. Instead, what we do is we drop the 8, And since it's an 8, it becomes sulfuric acid. What happens if instead it was H2SO3? This right here would be sulfite. And so this becomes sulfurous acid. Okay? That's why HClO3 is chloric acid. HClO4 is perchloric acid because they end in 8. Sulfuric acid because it ends in 8. And nitric acid because it ends in 8. This, an example of nitric acid is this. Since that would be nitrate, it becomes nitric acid. Whereas if it was HNO2, let's make this a 2 now. This part would be nitrite, so this would become nitrous acid. So, what happens, we've been talking about, those are all ionic bonds, but what happens if it's a covalent bond? So right now we're talking about usually 2 nonmetals binding together. Here you have to use prefixes. Okay? You always list, or usually almost always list, the less electronegative atom. That means the one that's on the left-hand side of the periodic table, or further left on the periodic table, followed by the one that's on the further right of the periodic table. Okay? And you have to get prefixes. The only time you don't get prefixes is if there's only one atom of the very first element in the compound. I know that this sounds really confusing, but if you've already been doing this and you just didn't know it, okay? And so I'll give some examples. Hopefully they'll explain it better. But the prefixes that you just have to memorize these are mono for 1, di, tri, tetra, penta for 5, hexa, hepta, octa, nona, and deca. That's 1 through 10. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So let's just do a couple of examples. I'm going to do one that you've already been doing all along. CO2 versus CO. These are 2 different compounds. CO2, we name the first element, that's carbon, and oxygen would be oxide. But if you just stuck with that, this would also be carbon oxide. And since there's only one carbon, you don't say monocarbon. But what is CO2? What do we call it? We call it carbon dioxide. Whereas CO, for example, the poisoning, like if you locked yourself in the garage with a car running, which please don't do that, is monoxide. Please notice that if the word begins with a vowel like O or A, we typically drop. We wouldn't say monoxide. We drop that one O. But I don't take off for spelling personally. So, not in this instance at least. Carbon dioxide, carbon monoxide. Let's do some more examples. This is P2O5. Now we have more than one of the first one, so we have to say di. This is diphosphorus. Phosphorus. And that would be penta, but we usually, since the next word starts with a with a vowel, we say pentoxide. What if it was something like this? Okay, let me clear off. BF3. We have boron, because there's 3, fluoride. Let's do another example. Let's see. CCl4. I want to give you a moment to try to come up with a name. The first one would be carbon. And it's going to end with chloride. But what's the prefix for 4? It's tetra. So this becomes carbon tetrachloride. Okay, so here are some other examples. Once again, if the prefix ends with an A or an O, the name of the element begins with a vowel, then you often combine them into just one. So that's why dinitrogen pentoxide, for example. And on your own, in the PowerPoints, I've included other examples and problems for you to work on, and I've also done the strongly suggested problems at the end of the chapter. This should conclude the lesson on how to name various compounds, and once again, I apologize for the length of the video and the fact that there's so much just rote memorization. But make sure you memorize the prefixes and then the common anions and common cations. See you later in class.